Guys, so in this is exploratory data analysis. What does that mean? We have been talking about that. It is looking at what the data is saying, not making predictions, not searching for hidden patterns, but seeing what is quite literally there in the data. And if you summarize the data, visualize it, uh, arrange it properly, you can see quite a bit of information in that. It is remarkable how many things you can see just by looking at the data. And that is where the history of this field is, like Florence Nightingale's example, and all those other examples are of people who just gathered data, the right data. And once they gathered the data, it was simply a question of seeing the data. And that is exploratory data analysis. So this is why I quote Galileo here at the top, which, and this quote means a lot to me. All truths are easy to understand once they are discovered. The point is to discover them. And that is exploratory data analysis. This is the definition given by John Tukey, perhaps the father of modern data analysis, with his landmark book in 1973 or something like that. And this is the definition that he gives. So anyway, in this thing, I've rearranged this thing a little bit. I put the exploratory tools first. There are two ways of doing data analysis, by using each of the functions and so on and so forth. And these days, there are all these automated data exploration tools. Like, for example, the Data Explorer in R and the Pandas profiling in Pandas. And if you are in the cloud environment, each of the cloud environments are competing to create their own specific automated data exploration tool. You upload the data and they'll give you some basic exploration of it immediately. So this is it. All data exploration starts with a data frame. We start with the data frame. We manipulate all the things in the data frame. A data frame is a rectangle. It's rows of data, each end with columns. You think of it as a spreadsheet. It's sort of like a spreadsheet. Now, data frame support comes built in with R, but in Pandas, in Python, you get it through the Pandas frame. Now, when you do that, you have a data. Now, what do? There are all sorts of ways you could be manipulating the data. After some time, people thought about it, and they said that, see, we need two things. We need a standard representation of data. It is called the tidy data. It's a pretty important concept, tidy data. Once you have data in a tidy format, it's sort of, you can apply a mini language to it with a specific small grammar. And that mini language is the language of data manipulation. So people call it a grammar for data manipulation. It means you just have to know a few functions, a few commands, a few things to operations on the data. And if you know those operations, they're usually called the verbs. With those verbs, you can do any complicated thing by a judicious combination of these or sequencing of these. And some of these verbs are mentioned here. You select. What does select do? It just picks a few rows of the data, select columns of the data, and people call it data projection. Then there is data restriction, which is the filter. Now, then there is mutate. Mutate helps you add new features or alter existing features. You can add new columns to the data. Arrange is a way, typically example of arrange is sorting. You can rearrange the data based on certain criteria. Summarize the data gives you a summary, like for example, the median of any of the columns and so on and so forth. Distinct obviously removes duplicate rows, counts the number of rows. And from machine learning perspective, and by the way, today we are really going to get into machine learning now, sample and these are ways to get fractions of the data. Group by is to group by a certain feature. Right? So these are basic operations. Then you have inner join, left outer, right outer join, intersections and unions. Now, those of you who are familiar with SQL would realize that there's almost an exact parallel to the SQL grammar. All of these things are part of the data manipulation language, DML of SQL. And it is really great. Yes.
Can you make your the percentage is 75.5, so the text is really small to read, at least for me. Can you make it 100% or 100% should be okay?
Okay, I am going to.
Perfect. Yeah, it's perfect.
It's perfect. Here we go. So these are the statements that you can use. And familiarity with SQL, those of you who are familiar with SQL know that this has almost a one-to-one mapping with what you do in SQL. Those of you who are used to functional programming, either in Java or Scala, would once again recognize that all of these verbs, these are essentially things very, very close to functional programming. It's a there you have the map, the flat map, the reduce, and summarize is like sort of the reduce and so forth. So count, sort, and so forth. So these are all things from there. Very, very close analogy to SQL and all that. So that is that. With this, can you do?
Asif, I have a question here. So when we deal with the datasets, does these grammar, the commands that we do to explore the dataset varies depending on the sample size?
No, not at all. And that's the point we are saying. It is, let me repeat what I said. If you just learn this basic grammar, any data set, irrespective of its size, its shape, you can manipulate. First thing you do, you bring it to the so-called tidy data format, a standard format, which is easy, and I'll explain that. And then once you have then you just need to know these very few words, and you're fine now. It is like, in every language, you have some basic words. And once you have mastered the vocabulary, the common vocabulary, you can write, a legal document, you can write a novel, you can write a technical document, you can do anything. The same is true here with data. It's a very important concept. Bring it to a standard format. And then once it is in standard format, you have tamed the beast. After that, you can do whatever you want with just a few operations. It is one of the things actually that's not emphasized strongly actually in most of the machine learning books, that there is a systematic way, and if you approach it, it becomes very, very easy and very powerful dealing with it. And it is language independent, whether you're doing it in R or you're doing it in Python, or you're doing it in Julia, or you're doing it in Scala, Java, doesn't matter. It is the same, essentially the same grammar, with minor variation, essentially the same grammar. And you just need to bring data to a standard form that is called a tidy form. And then you'll be able to manipulate that.
Okay, thank you.
The only difference that would be that suppose you have data at vast scales, then you wouldn't create a pandas data frame. What you would create is a so-called a PySpark data frame. Right? Use libraries which are more conducive to huge size data, but the grammar is more or less the same.
Yeah, that's what I was asking. So, okay, the underlying tools might be varying, but what you're saying is the commands that we use to explore still stays the same.
Exactly. And so what you need to do is master one thoroughly, right? Which is why I started this whole thing with data exploration. And it is the first time, by the way. In the previous times, I would just start straight with machine learning. And what I realized is that as people did more and more advanced stuff, I would see that they could do the machine learning part, but they were all struggling with just manipulating the data wrangling. And so this time I decided that it's a very important thing and I shouldn't miss it. And that is why it is. That's why I'm here to write it out for you guys. So what is tidy data? Tidy data is actually a very intuitive way. It says that each row should be one observation. So for example, let's take weather. At any given hour on a given date, in a given place, let's say Fremont, you observe the temperature, the wind speed, the wind direction, the pressure. So these are different measures or different features of the weather. They all help quantify that one observation, weather observation. And so it should be there in one row of weather data. The columns of the data should be, of course, the features. Like, for example, when we talk of the weather, the features should be the temperature, pressure, humidity, wind speed, wind direction, and so forth. Right? Those would be the features of the weather. And the intersection of a row and a column is, of course, a cell. A cell is obviously what is the temperature on a given at a given hour on a given day at given city, say Fremont. It would be a value. Let's just say it's 57 degrees Fahrenheit. Right? So that's what it would be. So it seems that what is the big deal? Isn't all data like that? The answer to that is actually data doesn't come like that. Data comes in all sorts of ways, and it comes in so-called wide format, as you will see in an example. It comes in a lot in a format that we want. Guys, 1 second. I'll put you on mute. I'm getting a call from support vectors custodian. So in this particular example, you'll see that the weather data did not come in that format. So our first job is to put it in that format. This is particularly true. Data comes nested, as JSON. So it will come as hierarchical data. XML data can be hierarchical. So data comes in all sorts of formats. But so your first task of data exploration is to put it in a tidy data format. And it's important to do so. So do that. Once you have done that, then after that, dealing with it becomes much easier. So here I take the example of weather data. This weather data set, and here's the link. Guys, actually work out these labs. And I didn't release the solutions so far, but I'm going to release the solutions today. I will post both the R and the Python notebooks, Jupyter notebooks, to our ML100. So you can follow through, but ideally try to do it on your own before looking at the solutions. So here data comes, as you notice, we are getting 1, 2, 3, 4, 5, 6 spreadsheets. This is very common. You want to do an analysis, data, you'll have to pick up data from many different sources. Usually it is not clean data, somebody has given it in the format that you want. So you take data from all of those and then you start your journey. First step is make it tidy in the format that you want. So what can you do? Let us first look at the data for any one thing. For example, let's look at the data that is there for in the city data. What does it say? This is the city, name, country, longitude, latitude. Very useful. That is the city data. Then we look at so is it in the tidy format? If you look at this data, guys, would you say in a tidy format? One data item is one row. Datum is one row, and the columns are the features of that datum. Anyone?
No, it's not in the tidy format.
And why would you say so? Let's say take a city like San Francisco. Don't we have all the features of San Francisco in columns? The country, the latitude, the longitude.
Not by country?
No, no grouping by country. It's just looking at rows of data and asking, is each row about one particular context? One particular.
It is tidy. It's tidy data.
Yes, it is tidy. We would say that this is tidy data. The way to do that is to just read one row and say, is it about one thing? Yeah, Vancouver, Portland, San Francisco, one city. These are the features of the city, which country the city belongs to, what is the latitude and longitude. In contrast, if you look at the temperature data, then you get a bit of a surprise. What you see is on a given day, you are getting these cities in columns. And for each in each column, you are getting a value, which is the temperature on that day. Now, if you're alarmed with 284, it is in kelvins. So to make it centigrade, just subtract 273, and then it will become centigrade. And then, of course, you can convert it to Fahrenheit. Might be a good exercise to do that. But most scientific data is in Kelvin. So this is it. Now, would you call this a tidy data? For example, for a given city on a given day, is the data one row? The context is at a given time, in a given city, I'm getting the temperature. That should be one row. So would you say that it is in that format, guys?
Yeah.
No.
No, it is not, because
See, look at it. There can be arbitrary many cities. What it means is that this table can be arbitrarily wide. It so happens that in this data, there are only about 32 cities. But in technical terms, I mean, if you think about it, the number of cities can be arbitrarily large. So it can be a very, very wide data set. And the context of San Francisco, the same example, if I want to know in San Francisco on a given day, what is the temperature? I won't get it in a one row. The row contains the temperature of all other cities also. Right? So it is a concept, actually. It takes some time to grasp, guys. Wide versus long. People who are very good with Excel, for example, they call it pivoting the data. So a long format and wide format, people often use this language. Because when you look at the Excel spreadsheet, or when you look at data frame, you can immediately get a hint of it, because the wide format data will be very wide and not so long. Whereas the long format will be very long, but the number of columns will be relatively smaller.
But is so the way we say the above data set, it's not a tidy format because it depends on what key you've selected to analyze the data, is it not?
Yes, so the key here is the context, and let me use the word context. I want to know about San Francisco at this hour on this day. So will the data be there in one row? Because my context or my key is San Francisco at this hour today.
Right. Okay.
So from that perspective, it is not in the format that we would want. It is in a wide format. And it's a good point that you brought up. It's context dependent. Yes. And these guys do this so that you get a way to handle it. So what do we do? It turns out that you can do this data, you can convert it to long format quite literally with, okay, where am I? One line of code. So in this line of code, I hope, is there a way to minimize this? Oh, goodness. Let me take care of the notifications and move this aside. Good, guys. So you take the raw temperature data, which is this data, and usually for these set of operations, these libraries, both R and Python, pandas, they have excellent support. You can convert from one to the other format quite literally with one line, but you need to make yourself familiar with the syntax of that. Play around with a few examples, see if it becomes second nature for you to do that. What usually will happen is, first time you'll read it, it will be confusing a few times, then it will begin to make sense. Then gradually you'll write your syntax down in a notebook or some online notebook and keep referring to it. And after a little while, it becomes second nature. You know what to expect and you just use it. Right? So this is it. In one line, we convert it into tidy data format. You see that? You take the raw temperature, and you pivot longer. And what do? By city and temperature. The value in the cell has to be the temperature value. The column has to become the city, and date time has to be left untouched. So when you do that, data comes now in this form. So here are a few rows of data. Now let's look at this data and see, is it tidy data? If I want to know, for example, what was the weather in San Diego on 1 p.m. on that particular day, 18th of June 2013, can I see it as one row of data, not see the data for other cities or other times? Do you see this, guys? Would you say that this is in tidy format? It's in the long tidy format, isn't it? Is this making sense in practical terms? So read this, guys, and in your book, on the two books that you have, one of them was the pandas, every man's introduction to pandas, everybody's, whatever, the pandas book, and the R book, the R book that I referred to you. Both of them, they do have a chapter dedicated to tidy data, because it is an important concept. Not many books talk about it so carefully, but it is actually very useful. For example, in my team, when people do data analysis, it has become for them a second nature to quickly come to the tidy format and realize that after that, everything becomes easy. So I'll show you how easy it becomes. What we did with temperature, we can do the same thing with all the other things like pressure, humidity, wind speed, wind direction, all the other temperature attributes or features. We can do the same thing. So we will end up with all sorts of files, different CSV files, all of them in the right format, right, in the tidy data format. But then suppose we want to stitch all of those together into one file, right, one data frame, the weather data frame. What do I need to do? I can join on the date, time, and the city across all of these files. So I will suddenly end up with, and this is the inner join that you see me do here. Those of you familiar with SQL would immediately recognize the syntax. If it was a SQL, you would say temperature, inner join on pressure, inner join pressure on blah, blah, right? On this field. It's a very similar syntax. You do the join, and at the end of it, you end up with this wide table. Not this wide table, sorry, with this complete table, which is still in the tidy data format. It's a long table with lots of values, because as you can imagine, the combination of date, time, and city, you will have a lot of values. You put all those values together, and you get this table. Are we together, guys, so far? I need some feedback, guys. Let me know.
Yes, sir.
Yes.
Very good. So read these things, guys. I've taken some trouble to write it out. And because, see, what I'm doing is, over the years, you do all of these things. In practice, you lead teams. You begin to see a pattern of what things are, in practice, more useful. That's what makes your life easier. And I'm putting all of those things here. So yes, we can do that. We have data. And now what can we do? Once data is in a tidy format, I want to just give an illustration how easy it is to do things like this. Now what I'm going to do is find the median temperature, median pressure, humidity, wind speed, wind direction. All of these I'm going to find for every single city. Right? So every city has lots of readings across different days. I'm going to take the median of all of these values and show as a table, because I want to know in general, is Chicago cooler or warmer than, let's say, Florida, some city in Florida, Orlando, let's say. So when I want to do that, just think if I had to find the medians in a data which was not tidy, which was in the old format, like this format, how tedious it would be. You would have data across multiple files, and you would have a huge trouble managing the columns and doing it. In general, I mean, you can do it, but it would surely not be as elegant and as simple. It is literally one-liner. You realize that one single line of syntax, well, I've broken it up into multiple lines for readability, as you should, but it is still one statement, one assignment. In one line, we have computed it all. You see that, guys? And not only that, I've even sorted it by temperature, median temperature. Right? So again, those people who have been doing Spark or functional programming, this should look pretty familiar. And those people who have been doing SQL, again, this should look pretty familiar. Group by, you all know, summarize. Once you do group by, then you can find all of these values. Then this is a sort at the end, sort by. So if you were to look at this table, for example, would you be able to tell whether, let's take which is the coldest city in the data set in general? Just as a basic example, can you tell which is the coldest city in this data set?
Montreal.
Montreal. And you can then go down to the bottom and see which is the warmest city on average. It gives you some intuition, isn't it? Which is the, for example, if you look at wind speed, you realize that, all right, you have a fairly good wind out here in this place, and some other cities are not that windy. For example, Portland seems to be not so windy, and so forth. So you can answer these questions. You can look at humidity and see which is the most humid city and answer questions. Now, I did this exercise in R. Right? Those of you will realize that this is R language. But how different is it to do it in Python? So let us just review the R code. What we did is in R, first, we read the data. Let's see, yeah, we are reading the data. Let's look at its Python equivalent. Here I'm reading the data in Python. Does it look more or less familiar, guys? Read.csv has become pd.read_csv. Looks simple to read and easy to understand, guys, in Python.
Yes, sir.
Similar. One of the beautiful things is that if you follow a structure like a sort of a grammar of data manipulation in a tidy data format, you will become equally fluent in both R and in Python. Quite literally, because these are just two dialects of doing the same thing. Now, one of the things you notice that I tend to create these tables with a certain bit of aesthetics. Like it's something that you should do. See, ultimately, you use your data analysis to tell a story. Right? To the extent that we do that, here is an example. This is a very lovely package in R. It is called Cable Extra. And you can, maybe Cable Extra, I forget what the right pronunciation is. And what you can do is in a very systematic way, it is like CSS. What CSS is to HTML, you can do that. And it does essentially the same thing. Another covers, I guess. It produces CSS of some sort. So that when you write your tables, you notice that my tables have headings and they have below, right? This is literally how it is produced by the R code. So it is something worth doing because, again, anyway, I started out by saying that with data, you tell a story, whether you just do exploratory analysis or you build sophisticated prediction models or clustering and pattern recognition. At the end of it, you need to bring it down to the level of, real people, people who are not data scientists. And it has to mean something to them. So you have to tell a story. And that story is the story that is buried in the data. You have to uncover the story and tell it. And so presentation matters. Professionally, it matters a lot, how good your presentation is. One very nice way, a mathematician friend of mine used to say that, see, we write theorems and all of these propositions and theorems and corollaries and so on and so forth. And it is all very abstract. But The moment we visualize it and we put it out, all of it suddenly becomes very real. So the beauty of mathematics is in visualization, especially in data visualization. So take it like that. It is the art of our fields, how well we present it and visualize things, do that. So here I'm going to do the same analysis in Python. This is it, the city data. I'm using the syntax of pandas. Now, how do I beautify a table in pandas? Well, it turns out that in pandas, it comes, the ability to style it in HTML comes built into pandas. It's one of the things people don't realize that you can style. In fact, when somebody asked me a question, how do you show, what was the question? Anil, it was you, isn't it? You asked the question, how do I produce that graph? In a table, how do I show a bar chart built in?
Yes.
And if you remember, it was just a one-liner that I sent back to you, isn't it? And that is the power of these libraries, guys. In the right way, they have all these hidden gems in them. You can beautify it. You can literally embed spark graphs and bars, little bars in the data itself, in the tables themselves, and it sort of comes alive. Right? It becomes more informative. There is I mean, ultimately, it conveys, you're trying to explain or show something to people, and it helps you convey that. So this is it. Now, how do you pivot or how do you convert it from the wide format of data to the long format? Very simple. The specific pandas thing is called melt. Instead of pivot, it's called melt. But do you see, guys, that it is exactly the same, city and temperature? Do you see how similar the syntax is between pandas? And let me show you the R syntax just for reference. There's the R syntax. Yeah, guys, look at this. Raw data and pivot longer. Date time, city, temperature. These are the three fields you mentioned, isn't it? Now you go to the syntax for R, and do you see that it is exactly the three guys? Date time, city, temperature. Right? It helps you pivot it into the long format. And then the join syntax looks practically identical. The only difference is in R we use the word by, and here the attribute is on. Very small differences between the two, which is one reason you should, I insist that people learn both the languages in the syntax. So once you have this data and you have cleaned it out, like for example, date time, you change it to capital letters and so on and so forth, and you sort it by city, you can see all of that. You can see data, again, in the same way, formatted. And how do you find the median, for example, the same statistic? Exactly the same. You group by all of these, you find the medians in a couple of lines of code, and that is it. Very easily, you have done that.
Asif, one question.
Mhm.
So in Python, we are actually just getting different CSVs for temperature, date, humidity, everything, right?
Right.
So, but what if the the table itself is already created, but it's in the byte format? How do we get it back in the tidy format
Oh, that is
if it's
easy.
not separate
Even
CSVs?
each of these things was already there. Once you get used to this, this pivoting, the concept of pivoting, all
Mhm.
you have to do is pivot it into the long format.
Oh, I see. So even if it's already there, we can melt it into using
Yes, the
the.
word melt, pivot, these are all synonyms. And these are very powerful things. In fact, when I interview people in my team, I'll start out by deliberately giving data in the wrong format and just see how they handle it. Do they just struggle with that and do a machine learning exercise with that, struggling all the way through, or do they actually pivot?
Mhm.
Right? And it's just a very basic thing to see how skilled people are in data wrangling. Why is data wrangling so important in machine learning? The fun stuff, the machine learning part, believe it or not, it will take the last 20% of your time. 80% of the time goes in data wrangling. gathering data, wrangling with it, putting it in the right format, tidy format. So what you are learning is actually, believe it or not, here's another way of saying it. In real life, you have, if you do this labs, you would have learned 80% of what you would do, 80% of the time you would spend doing this in the workplace. Literally, it's a fact. It's not an exaggeration. You would spend the better part of your life in data wrangling. So do not be in a hurry with machine learning. This is where you need to become so fluid, so fluent with this, that you see the data and as a second nature, you can immediately go about cleaning it and pivoting it. And Nisarg, you were there in the Nisarg and Anil, some of you were there in the boot camp in the previous thing. You remember that there's more to it. A missing value handling, like outlier treatments, outliers and special novelty treatment, isn't it? And anomaly detection, and so on and so forth. So there is a lot, but we have started. We have started dealing with the data, and we'll do more after this. So this is it. So this is tidy data, guys. Huh? With that, then I go into the example of Florence Nightingale. She is obviously a most remarkable character. Not only is she the mother of nursing, considered the mother of nursing, because she started the profession of nursing literally as a modern profession. It started with her. She created the first nursing hospital and nursing school. And she learned all of that from this data that she gathered during the Crimean War. And what she observed in this data is far more people die, of course, from malnutrition and bad medical conditions of those days, lack of hygiene. Lack of hygiene was a huge thing, dirty places. So than from actual bullets or in wounds, battle wounds. It was a remarkable and eye-opening discovery. And by the way, she is quite remarkable. So she's also considered essentially the founding, or certainly the pioneer in data visualization. This word visualization, remember, predates computers. It's hand done, and she did it. And she went and presented it to the powers that be in London. And of course, the rest is history. The whole practice of modern nursing started. So this is that. And if you actually look at this data, you will be surprised. So I'm doing this now, I'm taking examples. How do you read this data? By the way, one thing that people ask, how do I get my graphs and plots to look so good? Well, I wouldn't consider them too good. People who are experts with this, aesthetics, they do a much better job than I do. But mine is probably better than the novices. So here are some of the tricks. I use LaTeX in the text and so on and so forth. And you will see some of that in effect. So I already set the figure size, I set the style of the plot, GGPlot, and so forth. So I'll take an example. This is the way you would do it in pandas. Now, in this notes, what I've done, guys, is I've alternated between R and Python. I've deliberately done one example in Python, then another example in R, another example in Python, and so forth, except the weather dataset, which I did in both, just to illustrate. And the idea is you should also do it in both the languages. In fact, you should do each of these examples in both R and Python. So here, we start with Python because you can tell the pandas data frame. This is a summarization of the data. And if you actually write the data, it's just 24 rows of data. You see that? So essentially, you can say that modern nursing started with 24 rows of data. Isn't it quite remarkable? Now, one of the things I wanted to say that, of course, I'll leave it to you to do the exploratory analysis for that. And you can do that, or you can just use the data profile, profile report, pandas profile report command, and it will produce the whole report. Now, those of you who were here in the last session that we held physically at Support Vectors, you realize that you had finished this part of it. Likewise for Jon Snow. Jon Snow, I've given you a hint, do it in R. Right? You see the data is in R. You can use these data sets and do it in R. By the way, all R data sets can be imported into Python directly. Scikit-learn gives you a direct support for R data sets.
Oh.
So you should know. So there is a very, very strong cross-pollination between R and Python communities. They are like, um, you do something, I copy, then I do something, you copy. It's sort of almost completely at parity. So I don't get caught up in all these debates of which is more powerful, which is the right one. Do both. So likewise, this is the Galton data set. Again, I believe I've used pandas. So again, alternated. Florence was in pandas, Python, uh, Galton, I left it. I mean, the John Snow's data set, Calder data set, I left it as exercise for you in R. This is again in pandas. And very simple. Galton's work is regression towards the mean. It is this concept of regression towards the mean is profound, guys. Its influence or its impact is way beyond just data science. One of the greatest historians of statistics and a great statistician in his own right, Stephen Stigler, who was also a great sociologist, great sociologist. So he used to study scientists as a tribe. If you consider them as a tribe, what are the behaviors and manners and practices of scientists and so on and so forth. Very interesting fellow. So he has written one of the books, The 7 Pillars of Statistical Wisdom. Regression towards the mean is one of those pillars. It is also a concept that our mind has tremendous difficulty grasping. When it is staring us in the face, we don't see it, and we ascribe all sorts of causal reasons for it. And so therefore, this data set, we must at our time do the Galton data set sometime in our life. It's really worth it. If nothing else, to drill this into our head. What is regression towards the mean? So this data file, by the way, is again there in our GitHub. Right? And by the way, if you want to go and look at this article, right? Do you see that in blue? These are all hyperlinks. If you were to click on this, it will, for example, open up you see, you can, well, okay, it takes you straight to the article, the original article, and you can read online for free and so on and so forth. Get started. Well, I suppose I have an account, I didn't notice. But if you just Google for this, many people have posted the PDF online for it. So this is it. And then Stigler's article, by the way, is very, very good. I must highly recommend it. It's a lovely article. Once again, this is again freely available. Download PDF. So if you download this PDF, you can, okay, I have accounts on the other machine, but yeah, you have to do all this thing. You just Google this up and you'll find this article available as PDF, maybe on Stephen Stigler's homepage or something. So that is that. So what is this data? You have families with father, mother, gender of a child, the height, kid, male, female, and so forth. Right? So you have this data, you can compute statistics of the data, and by the way, is this in tidy format or not? Let's take a quiz. Is this data in tidy format? What would you say? What does each row of data speak of?
It speaks of
One family.
Yeah.
One child in a family. So if you look at one row, it is one child or one offspring. It says that it belongs to family number 1. So the family number 1 seems to have 4 children, 0, 1, 2, these 4 children. Then in each of them, the father's height is the same. This is the mother's height. For each child, this child seems to be a male. So this column is meaningless. Male is 1, female is 0. It is just a encoding. Height of the child. Right? And obviously, this speaks of this family has how many children? So these are the heights of the 4 children in that family. So each row is a child. So the context is very specific, isn't it? So it is in tidy data format. We can describe the data again to see what is the average and so on and so forth. So for example, these are all in inches. Let's look at the average height. 50%, the mean height. So clearly the mean height is 67. It is the averaged over both male and female, right? The data seems to have a little bit of asymmetry. About 51.7% of the people are boys, and 48.2% seem to be girls as children. Right? And then this is the average height and so on and so forth. In general, what can you tell from this data? Are fathers taller or mothers taller by just looking at this data?
Fathers.
Fathers, right? The average weight is much more than mothers. So this is it, guys. You know, you look at data, this looks like very trivial thing to do, but it is worthwhile doing that. And then, of course, you make graphs and so on and so forth. So you see me here make a graph. And once again, I assume, so by the way, guys, when you make graphs, it may not look like this. So why are my graphs looking different? The reason for that is it has to, and I'll come to, actually hold that thought in your mind because it is in the document. When you read it, you'll see this in the chapter I mentioned about. So this is, do you see how minimalistic it is? The grids are missing and so on and so forth. It's quite minimalistic. And these days we believe it should be like that. I will talk more about it. So this shows you the height distribution. Clearly, the men are taller than women on average, right? This is a violin plot. It is very much like a box plot, just more a prettier version of the box plot. A little bit different, actually. It's not exactly what it talks about, but I won't go into the technical detail. Then see what happens typically is that you want to know the histogram, you know, the frequency charts of the father by height. What are the different heights of the fathers and mothers? And the scatter plots by mother and father height. Right? So clearly you see that there is certain degree of correlation between mother and father height. Right? Not a very strong correlation, but there is some correlation. Okay. And likewise, the children, height of the children are related. Then male tend to be taller than the female again, once again. And these are called density plots, kernel density plots. What they give you are the contour lines. They give you a sense of how the data in 2 dimensions are grouped together. It is a topic that I will cover one day, but intuitively, it is like if you think of all of these points of men and female as clusters of points, where is the peak of the cluster? Like how densely are they sort of located? That's what this kernel density plot KDs are. These are called kernel density estimators. We'll talk about it more when we get into the machine learning. But at this moment, take it at face value. Then we look at the correlation. What is the correlation of the factors with each other? Do you notice that any child, height is it ever perfectly correlated with the height of the parent? Father or mother? What's the correlation of a child's height, of the height? Height's correlation with father and mother is just pretty small, right? 28% and 20%. These are small correlations. So you do, and that shows in this data. You can see that the correlations are there, but they are very small. Data is scattered. So I've given a homework here, guys, which is a sort of worth saying. I'll just mention what the homework is. Notice that the correlation between an offspring's height to parent's height is never perfect. A perfect correlation would be what value, guys? Anybody?
1.
None of the values are 1 except the diagonal, which is like self-correlations. So now the thing for you to do is to reason from there and explain the phenomena of regression towards the mean. So this phenomenon can be explained. The roots of it is in this, the fact that regression, the correlation is not perfect. Now, if you recall, I'd given this explanation in the class. I'd given it to you using correlation, and then I'd also given it to you in terms of the regression equation. Right? Think through, see if you can reason it all the way, recall the explanation. This one exercise is really worth doing, right? Because it's an observation. It will tell you an observation that most people don't know. First of all, most people don't know that there is regression towards the mean. And then if they do know regression towards the mean, they don't know why does it happen. Right? So the statement that you should discover is regression towards the mean is a direct consequence of imperfect correlations. So once you have thought it over, then you can look for a very detailed article. This particular article of Stigler, absolutely, definitely worth reading. And again, I'll click on it and it should take me, well, it takes me back to this journal. And then there is a book by a Nobel laureate called Daniel Kahneman, Thinking Fast and Slow. Fast and Slow. I don't know if anyone of you have read it. Very, very interesting book. He talks about two kinds of mind, how a mind reacts. A fast thinking mind and a slow thinking mind. Usually fast thinking mind is the one that quickly gets into trouble because it sort of comes to the wrong conclusion very rapidly and doesn't realize that you have used your fast thinking to come to a bad conclusion. And you need to do some slow thinking and so forth. It's a very interesting book. So if you want to read it, he talks about regression towards the mean. Right? So in the community that looks at data, this regression towards the mean is a big thing, guys. Really worth knowing, which is why I started this entire workshop series with it. We'll never again talk about it because we have to move on to other things. Today is the end of data exploration. In fact, today I would like to request a longer session till 10:30 because we have to do machine learning. But for what it is worth, I want to cover this document. So pandas profiling once again. So what does pandas profiling do? One line of code will produce pretty extensive report, and you should do that. It will produce a summary of the data. It will produce the correlations. And it turns out that there are many kinds of correlations. I'll let you explore those in due course of time, one by one. I will be talking about that, but I've introduced you to the correlation by Pearson because he was the student of Galton. And he formulated that concept of correlation and so forth. So you can see all of this, histograms and everything. I won't go into that. Do it in your labs, right? Certainly do that so you can see it. Next, we move on to iris dataset. So the previous one we did in Python. So certainly this one merits R. This is it. I'm doing it in R. There's a very interesting history to this dataset, iris. Nobody, like all the data scientists in this field, well, of course, the field of science, almost everybody has started out learning machine learning. Well, that's a secular statement. Has started out in machine learning by doing this exercise early on iris. At some point, very early in their learning process, they have all studied the iris dataset. At this moment, we'll limit only to the exploratory analysis, no machine learning, but this is it. Really worth doing. It is perhaps the most quoted dataset in various articles in the field. Everybody comes up with a new algorithm and he uses that dataset quite often. It came about, there's an interesting history. A biologist just literally walked out to a colony of iris flowers. And in that colony, he found 3 species and he collected 50 data points on each of the species. He collected their sepal length, sepal width, petal length, petal width, and he got the data. So you can just go and get the iris data. It is again, I've posted it to our this. Once again, if you just preview the data, just in the raw form, do you see how basically bland it looks? So you can prettify it quite a bit and just bring in the library tidyverse. It will import all sorts of things in the world of tidy data. It will include bplaya, it will include GGPlot, which is the grammar of graphics, how to create beautiful graphics, and all of that. So here it is. You guys are familiar with this code by now. Here I'm doing. So what have I covered? I've covered the last column because that's the species. That is the species, and these are the attributes of that species. sepal length, sepal width, petal length, petal width. Right? So is this data in tidy data format, guys? Again, once again, if you were to ask this question, what would you say? Is it in tidy data format?
Yes.
Yes, right? Because this is an instance of iris setosa, and then we have the four measures, the four features. It is in tidy data. So how do I deal with this data? Well, I haven't done much. I've just taken an example. If you have it in tidy data, you can easily summarize the data, what we did before. By the way, in the flower, I put the pictures of the flower. And so you have to look a little bit carefully to see the sepals and the petals. This is the sepal and this is the petal. Right? It's a biologic thing. The big ones are the sepals. So when you look at the median, it's just worth observing. Let's look at iris setosa. Do you notice that sepal length is 5 and the sepal width is 3.4? And then petal length is 1.5 and petal width is very low. So if you take the ratio of these two, 1.5 divided by 0.2, you realize that it's a 7.5 times bigger. The petal length in general is bigger in iris setosa. So you can look at this picture and see, is the petal long and narrow? You can't make it out, but this is the long and narrow petal. So it speaks to the data. That's what it is. You can look at the picture and verify if these things are true or not. And if you look at Virginica, it has the widest petals. You know, of all of this, Setosa has the widest petals. And then the sepals, widest sepals. And the second widest is, well, they're almost close to each other in the sepals part. The petals part, Virginica has wide petals. And I suppose this picture is too small on your screen to see, but you do see the width here. So it's worth, comparing the data and seeing, does it make sense or not? Next comes to visualizing data. Now, visualizing data is a topic that I would say, people, just as, people can do data manipulation in a haphazard way, whichever way, they hack their way through, wrangle with it and hack their way through. But you can do it in a systematic way. In the same way, when you have to make plots, you can make these plots in sort of a haphazard way, hack this, hack that, and put a plot together, or you can do it in a systematic way. So there were so many plotting libraries, and every library had a different API. And then came a landmark book, which is a little abstract. It is called The Grammar of Graphics. It's actually a very good book. It talks about how all graphics can be considered sort of like a language. And you can speak the language with a very few words, with a very few, with its own fixed grammar, just as you can speak English with a fixed grammar. And if you do that, you can systematically build up a graphic, any graph, any plot, you can systematically build up. So that philosophy influenced actually at least two very popular open source projects, very popular. One of them in the JavaScript world is called D3. D3, yes. Those of you who don't know about D3, I invite you to Google it up at some point and see what D3 is. It is perhaps the most widely used data visualization library. It is based on the grammar of graphics. And the other, in the world of R and Python, it showed up as the library called GGPlot. So GGPlot, and here I've given the code to show how layer by layer you build up a graphic, as simple as this. We are showing the histogram of sepal length by count. Actually, I should fix this picture, it's not very legible, but that's that. Huh? So how do we actually, is it because not legible, or let me go to different view perhaps. Zoom. Really, view not show. Give me a Let's look at it. Oh, no, it's fine. Okay, that still could be clear. So if you look at this diagram, guys, what do you see? We are looking at a feature called sepal length for the 3 species of iris. For each species, we make a frequency plot, a histogram. Right? Histograms of frequency. Right? And obviously, it's bucketized by some bins, some from let's say 5 to 5.1. How many of iris setosa data samples were found, and so forth. So this is a frequency plot. Now let's see how it is built up. Those are called histograms. First of all, you think of it as layers, like as in Photoshop layers. You first take the first layer, GGPlot. It is the data layer. You just give it the data. In the second layer, which is the aesthetics, you specify your axis. What are you specifying? The only thing you need to do is provide the x-axis, which is the sepal length. So you just picked a feature, a column for that. And then you picked fill is species, like what is the fill color, and you do that. And then, so this is just specifying this, and the color. But what are we going to do now? We happen to do a geometry. So the way a grammar of graphics thinks, a histogram, a scatter plot, a line, and all of these are just different geometries to represent the data. And just by changing one line of code, the geometry you choose, you can represent the data differently. So here we choose histogram. Now you notice this alpha is equal to 0.5. Those of you, I just thought I'll let you know. Those of you who are good with CSS and HTML know what alpha is. What is alpha? Could anybody tell me?
Transparency.
Yeah, it's the level of transparency. One of the things you should do is, if you fade it out a little bit, it looks aesthetically more pleasing. It looks a little bit too bold colors if you don't give transparency. So I would highly encourage you to always play with transparency to create a good effect. Right? And then you notice that I have added a theme to it. So it's the next layer. And none after this geometry, these things are not really needed. Right? It is good to have. I added a theme called Tuft. What this theme is and what in the world Tuft thing is, we'll come to in a little bit. We're coming close to it. And now we add a label. So here, label, I've given count as a label. Otherwise, it wouldn't have been there. So you see that how systematically I'm adding, think of each line as a layer, data layer, aesthetics, geometry, theme, and then touching up the theme, fixing the axis labels and this and that. And you could add a title and whatnot. So this is the grammar of graphics. Believe me, guys, people have created absolutely stunning visualizations using the grammar of graphics. D3 and GGPlot, by using that, either of these two, people have created beautiful, beautiful visualizations. In fact, if you go to the D3 website, D3, and the person who created this is Michael Bostock, an amazing, amazing fellow in data visualization. And if you look at the gallery of visualizations that you can do, examples, look at this. All of these things can be done with just a few lines of code and a very sort of intuitive set of lines of code. All of these visualizations you can do. So I would highly recommend that whenever you want to create a data visualization, visit it, see how it is done, learn from it, and then do it. And whenever this code is, thanks to Michael Bostock, freely available, so you can, if that code suffices for your need, you can take it. And a lot of the places people just have used this. If you look at these visualizations, you would remember how many websites, you would recall that there are many, many websites you have visited which actually use these things. So, and there are many, many websites devoted to this sort of thing. And any one of these, let's go into any one of these.
So Asif, this is a JavaScript notebook?
Yeah, these are all JavaScript, done in JavaScript now, right? So suppose I take Sunburst. It's a hierarchical representation of data. Right? Let us see D3 at play. I mean, the grammar of graphics at play here. What do? You take a canvas. The very first thing you do is put a data layer. Do you see this, guys? A data layer. You put the data layer, and then you put the fill, color fills, and so what do you fill it up with, etc., etc. Right? And you give it some text. What is the text that you would do? And then after that, you're attaching. Do you notice that these are all styles? The rest of it is styling and so forth. Right? Append. You're appending some. You're doing some. Well, this one is a little bit complicated, but I hope you discern some of the structure that we talked about. Data layer, then aesthetics, then themes, or color and title and so on and so forth. You can do that, and obviously people have created a ggplot libraries too. ggplot showcase, R package showcase. Let's do that. Oh, I don't think this has that. No, this is just a. These are highly well documented libraries. People have done that. Tidyverse, beautiful visualize. All right, I'll just click on one of them. So here somebody has taken a data set and look at this. Yeah, see guys, see how he builds the data. He takes this file, he reads the data, then first thing he does is he says, okay, ggplot. Then he's going to bind it to a geometry, right? First plot, geometry, but then you have to give it data. So at some point you have to give it data. Usually I give data in the ggplot itself and then add geometry to it. After that, aesthetics. What are the X and Y axis? It leads to this. And then this looks pretty ugly, black and this. How can you make this chart better? You start now adding, make the dots smaller, right? Adding colors, right? And then obviously the next things would be, and you can scale it by log. You can do a scale distribution and so forth. I assume at some point he'll get into colors, I hope. Yeah, he's getting into colors and so forth. And do you see how systematically the visualization keeps getting better? At each point, he adds one more thing. To go from one to the other, he keeps adding things. So it is very additive. You can add sentence by sentence, and then it keeps getting better and better. You keep putting layers, as people who are familiar with Photoshop would say. So this is an example of ggplot. I would highly recommend you learn ggplot. And I mean, there are many plotting libraries, but it gives you a systematic way of doing it. And suppose you want to show not just sepal length, but you want to separate the histograms. So you notice that here all the histograms are mixed up in a single graph. It's a composite. Suppose you say separate them out. All you have to do you notice that you took the previous code and you just add one more line, one more layer called facets. It says by species, separate them out. Guys, are we understanding this? Give me some feedback. Are we able to understand this? Does it look familiar?
Yes, it's clear.
Yes, and it's very powerful, guys, to do that. Huh? So you can do that. And then, of course, suppose you want to say, I want to make a grid plot of looking at this by sepal length, sepal width, petal length, petal width. So there are many libraries that help you that have extended ggplot. You can do it with ggplot. It's a little bit more code, but people have written libraries on top of ggplot to make it easier. And one of those libraries is cowplot. And here's this usage of cowplot to do that. And there is also gridplot and other libraries are there, grid extra and so forth. People have added. So pick your favorite and do that. Now, one question that you should have in mind is, we are talking of all these libraries of R and Python. Where do I go looking for those libraries? And we'll come to that in a little bit. You can make, this is then box plot. If you have done courses in statistics in high school, these are your box plots, right? How do you draw the box plots? This is the way. Very simple. What do? You make 4 plots, one for each attribute, sepal length, sepal width, etc., etc. And you do this. Right? And you get. Now, you must notice that this is rather bare compared to the typical thing people have. They'll have all sorts of grid and so on and so forth. This minimalistic style is highly encouraged these days. So now that we have done that, we can do bivariate statistics. How hard is it? Again, very easy. We are still talking about iris. So we create a correlation. This is use the core function. It will produce the correlations. Right? Why only 1 to 4 columns? Because there are 4 attributes. The first 4 columns are the attributes. The last is the species. Then when you default make a core plot, it will look rather ugly. I mean, the principle, sort of what I call principle of least ink, or what Tuft says, is that you need to have a high data ink ratio, which is that data should take more ink and clutter should be minimum. So correlation is asymmetric. The correlation of sepal width to sepal length is the same as correlation of sepal length to sepal width. So no point in repeating any one of the boxes. So you notice that some boxes are missing. Redundant boxes are missing here. And how do you do that? Let's again look at this very simple plot. People say, okay, how did you get that? Right? When I do a default core plot, it doesn't look as pretty. So the answer to that is, let's see here how I do it. By the way, this is the clustering order. It's something I do in core plots. Ignore this part. Right? First of all, I do the correlation. I give it the data. Then I say that only have lower, because there's no need to have both upper, lower. If you don't give it, then it can show everything. Outline color white. Where is that? It is hard to discern, but there's white line separators for the boxes. And obviously here I'm going blow by blow, but gradually I'll move faster. Then one of the things I'm doing is I'm suppressing the x-axis title and y-axis title. It's redundant. Right? And then I'm giving it a theme. In the theme, I'm saying, all right, the element size should be, all text should be 16 points font, and all titles should be larger font, 24. So does that show for it, guys? Is this bigger font than the rest of the text here?
Yes, Asif.
So that is it. Actually, I'll make it more like 150. I think. So this is it. So this is how you make this. You use libraries. Then you can do more than that. Suppose you want to do this pair plots that I was talking about. Remember, we did the pair plots in in Python. So how would you do the pair plots in R in a pretty way, equally pretty way? This is it. You use a library called GGGalley, again based on GGPlot. And what do you think, guys? Does it look nice? It does, right?
Asif, I have a question. So the sepal length to sepal length should be a correlation of 1, right? So I didn't understand why there are 3 histograms there.
Okay. So here, right, it is a sepal length. Each is a histogram of one species. Setosa, virginica, and the other one, whichever.
Oh, okay, got it.
Those are the histograms. And this is, you literally see the distribution. So, you see this histogram here, and you see the data right here. You see that the data goes only this far. Right? For the pink one, it goes this far, yeah. And here it goes much more. So this is it, guys. This is, do I need to do more? Oh, yeah. So after all of this example, I thought I should leave some things for you guys at least. So this is the California house prices data set. Can you guys please repeat whatever you have learned in these notes and apply it to the California housing data set? Right? So in California, everybody seems to be very obsessed with house prices because for the vast majority of people, middle class people, it is a fact of life that our single biggest asset are our homes, if we have a home. If you don't have a home, then well, that's a different story. Quite often, our homes are our biggest assets. So when the economy does its ups and downs, we get worried, and we often keep looking at a house price. You know, Zillow is a very popular website, and there are many other websites who rank house, sort of give you an estimate of the house price. So I thought this data would be interesting to you guys. And this data is from the 1990s. You will learn something about how house prices were in 1990s and how house prices are spread out in California today. So do this analysis in both Python and R. And guys, send me your notebooks. Email me your notebooks. I will review and give you feedback. Are we together, guys? And if you need help, reach out to the TAs. Reach out to this Dennis, Prachi, Dennis. Reach out to them whenever you need help, or reach out to me directly. So now that's your work. Now I'll give you some basic tips, guys. This is an important tip actually from who is Edward Tufte? He's a professor at Stanford, and he has had a tremendous influence on the display of quantitative data. His book, A Visual Display of Quantitative Data, literally by that name, was sort of groundbreaking. He gives popular workshops, a bit pricey, but actually very good workshops actually, here in Silicon Valley and everywhere. If you guys get a chance, attend his workshop. You'll get a completely different perspective on how graphs or plotting or just data visualization should be. Now, one thing that may interest you, this document, do you guys like the formatting of this document? Anyone likes the format of this document? This document itself follows Edward Tufte's recommendations.
Yeah, I went to his presentation.
What's that?
I did go to his presentation.
Oh, you did go. How did you like it?
It was good. I don't know how much longer he's going to be giving presentations, though. He's getting pretty old.
Yes, he is indeed. So Edward Tufte says that graphic excellence is that which gives you the viewer the greatest number of ideas in the shortest time with the least ink in the smallest space. Do you see how much he emphasizes brevity and a minimalistic approach? What happened, guys, is that we used to actually, when we were growing up, my generation, distinguish between what we call a scientific diagram or a graph from art. Right? A line graph, a bar graph, or a diagram of a machine used to be minimalistic. It would show things clearly, they would be labeled clearly, but you would not add shading to it. Those of you who have done machine drawing would remember that you would do the plan elevation, side elevations. Well, today is the world of CAD/CAM, so perhaps you don't know what machine drawing is. But if those of you who do, remember that it was a minimalistic approach. All scientific data is minimalistic, represented minimalistic in journals. But somewhere along the line, you know, a data visualization gotten into the commercial world, and in the hype of marketing and whatnot, people started adding eye candy and clutter to the graphs. So unnecessarily, the bars began to look 3D. They began to develop gradients, you know, color gradients. All of you have seen this, isn't it? And all of that. And soon, when you looked at a graph, you weren't sure whether you're looking at a scientific diagram or a plot, or whether you're looking at eye candy or art. And there was overwhelming. I mean, I don't know. It was actually pretty much a mess. Many tools that help you do data, business intelligence tools and whatnot, they are to be blamed. Most of the data analytics tool at one time used to fall for that sort of eye candy in their widgets. You could make the graph unnecessarily a bar chart three-dimensional. You could add a third dimension, and shade, you know, gradients and whatnot. So it is completely against the grain of scientific data visualization, right? Or display. Keep it minimalistic. Your point is to convey a story and information, not to create eye candy. And one particular story that Tough takes, which is quite illustrative, is the Challenger disaster. So many of you know that at one point, shuttle, it blew up on the launch pad itself. So when it did that, people investigated what happened and why it happened. And it was the physicist, Richard P. Feynman, who found out the reason quite simply. He took an O-ring, what we would call a gasket, and he put it in cold water. And then he shows that when the temperature is low, it becomes brittle, it breaks. And so what had happened is that the seals had gotten compromised, and so fuel, a highly inflammable material, had leaked out, and there was a fire. So then the whole question is, how is it that it was not caught? After a lot of investigation, it turned out that actually there were a couple of engineers who had been saying that this is a problem. So they presented it to their management, but they presented it using a visualization that is hopeless, clutter. And their entire presentation is so convoluted, so complicated, that the upper management thought, okay, no big deal, we can go ahead with the launch. So from a data scientist perspective, did those guys succeed in their core mission of their data analysis? Would you say they succeeded? The analysis was perfect. It even showed it. It even made pictures and diagrams to show what was wrong or what could go wrong. But from the way we look at it as a data scientist, it was a singular failure because it failed to tell the main message. The data was telling a story, and they could not convey a very simple story, which was that at low temperatures, the O-rings will get compromised. As simple as that. It could have been conveyed with simple data and simple visualization. You see how it is and how tragic the consequences are when you don't do it the right way. Right? So something is sort of a cautionary tale. So this is about, so he talks about, Edward Tuff talks about the data ink ratio. How much ink did you spill to show the data versus the total ink used in the graphics? Did you add a lot of shading and third dimension and eye candy and a lot of tick marks and this and that, grid marks and so forth? So avoid that. Ask, is it absolutely necessary to show what is here? If it is not absolutely necessary, take it out. Now, it turns out that R is generally more mature, being an older framework. So obviously there is a tough theme that comes built in. You can add it to GGPlot, as we have been doing in the code. In Matplotlib, it's a little bit harder to do that, but you can still do that. People end up writing their own functions, themes for Matplotlib, which mimics the tough style. And if you guys are interested, I can give you the code from mine, or you'll find my code sooner or later. The other thing I do is the text that is there. If you look at the text that is produced by these plotting libraries, it is, in my view, very substandard. It is not the high quality text that one expects in a publication quality scientific journal. I mean, a scientific journal. If you write an article and expect it to be publication quality, it should meet that standard. Aesthetics matters. So. And in that world, generally LaTeX, there's something called LaTeX. It is considered to be the gold standard. Most physical sciences, mathematical disciplines, physics, math, and chemistry, and so forth, quite often, they all tend to use LaTeX. And computer science also, all the research papers tend to be written in LaTeX. So people like the formatting of LaTeX. It has a professional appearance. The good news is you can actually do it in your code. You just have to remember to, first of all, on your machine, have the LaTeX installed. On Windows, on every operating system, it can be installed. Do that. If you're willing to do that, then, and I've taken this example in Python here. Do you see that I've read some data set 2. By the way, this is part of your next lab, and we'll do that at some point. Data set 2, I'm going to visualize it. So first of all, I do this normal aesthetics, colors and this and that. Then you notice that I'm doing some things. Now, usually I do it not for every plot, but I do it in the top of my notebook so that it applies to all the graphs that will come, all the plots that will come in that notebook. But these are some of the things I do, family. You see this crucial line, use text is equal to true. If you don't have text installed on your machine, you will have to remove this line. So what does it do? Now, it turns out that R actually comes up with something, and this whole matplotlib comes up with this lovely thing called not R, Python and R has this Python and matplotlib has this lovely syntax. If you wrap a text with this R quotes, a string is just quotes, right? Font is just in single quotes. This is what you would call a string in Python, isn't it? But notice here, we have done something strange. We have put R before it. When you do that, then it is interpreted as a thing written in LaTeX, in the language of LaTeX. And this $x$ is a LaTeX syntax. What it says is X is a mathematical term, Y is a mathematical term. So write X and Y in mathematical notation. Right. And then I'll give you an example of what it produces. This is what we are aiming for. Now, I don't know if it shows through, but when you print out, let me go to 100%. Is this 100%? Well, not particularly. Somehow on this WebEx, it's not showing, coming out in full beauty as it would when you print it. But do you notice, guys, that this seems to be, there's a title. I've deliberately put a random title here. So this seems to be a sine wave function. Now, this is mathematical writing, right? Y is a sine kx plus phi. That's the equation for a sine wave. Right? This is the data. Obviously, I've added some aesthetics to it, transparency and whatnot. But sometimes to make a point, you need to put arrows and notes. These are called annotations. You put annotations. So these are annotations I put. And you notice that this notation here, X feature, it is, when you zoom into that, you will notice that this is actually fairly professional. Well, it doesn't show, I hope it shows here. Well, do you notice that it's sort of written in good fonts? All of this text is written in good fonts. So the code to do that is here. This is the code that will help you do that. All of these things. This is how you create an annotation. So there are two annotations, both of which are here. Right? This is the title. And you notice that in the title, again, I have put LaTeX syntax. LaTeX, by the way, I must warn you, it has a pretty steep learning curve. Like, while it is nice to say that you can do that, as they say, Rome is not conquered in a day. So as you are entering data science, don't try to do everything at once. So, so if it is new to you, by the way, is there anybody in the audience who is already an expert in LaTeX? If not, well, it is new to most of you. It's a language in its own right. It has a steep learning curve. It is a language for typesetting documents, typesetting. A beautiful language. It was created by the great Donald Knuth. He got so frustrated by the fact that mathematics couldn't be properly written in journals that he sat down and created tech. And it is, by many measures, perhaps the one library that has no bugs. For the longest time, it's a huge library, and used to offer $100 to anybody who would find a single bug in the text code base, the implementation of text. And it became very, very hard to find any bugs. So it is practically bug-free. It's one of the few software that is actually as close to bug-free as is humanly possible. There is a legend, there's sort of an understanding that things will keep getting fixed, but when Donald Knuth dies, whatever version is there will be declared the final version, and all remaining bugs that will be discovered will be called features. It's sort of a joke in the community. It's a tradition, and I believe they are going to follow that tradition. But tech is a grand, it's a grand language. Many of you don't know, but if you do want to get introduced, again, slowly. There are lots of tutorials on it. You can do that. And so again, now in Python, how do you create a grid of plots? We saw how to do that in R. Well, here it is. I've given an example code of how you would do it in Python. You see that, right? In Matplotlib, this is creating. And I'm reading 4 files, by the way, in a loop. This is a for loop. Oh, by the way, I should have shifted it. This is wrong. In pasting it here, the indentation went wrong. So as a Python code, this would actually, it should be indented a little to the right. I'll fix that. So anyway, this is the Python code. Read 4 files, and for each file, just plot the data. But the point was to illustrate how would you create subplots. So this is it, guys. So, and all of this, by the way, observe syntaxes in that. I use syntax. By the way, where are all these data sets? As a reminder, once again, it is here. In the margins, you'll find all the references. Now, and then we are done, guys. Another thing, some helpful cheat sheets. You're entering a vast world of data science. It helps to have some good cheat sheets. Now, there are many, many cheat sheets. What I do is, and I'll give you a way that I recommend people to do. When you're learning this, print out these cheat sheets and just put them on your wall or on your table, paste them to your table. So what happens is that whenever you need it, you can just directly look at it and you get that. Or, you can, if it helps, one tip that I give to people is, because these are PDF documents, you can convert them to images and so forth. Make them as the background to your laptops, desktops, workstations, whatever. Just make this cheat sheet the background image. So as you are doing data science, as you are creating your own code, it is very easy to refer. You just have to look at the background of your computer. And that does that. And so there are all these lovely cheat sheets. People have spent quite a bit of effort making this. Like, for example, Pandas is pretty extensive library. But if you look at the cheat sheet, do you see this, guys? Huh? Are you able to see my screen, guys?
Yes, sir.
So this is it. In one page, all the key operations are mentioned. How do you create a data frame? 3 ways of creating data frame, method chaining, reshaping data. Remember the pivot, the melt. It is there. How do you concatenate? How do you join and so forth? How do you summarize data? So it really helps having this cheat sheets with you, because it summarizes a lot of learning. You learn and then you refer to the cheat sheets. So I've tabulated all the major cheat sheets that you will need, and also implicitly the libraries that you will need, that I consider essential to this journey. Now, where do you go looking for documentation? It seems to be a vast world. Now, I've documented the 2 things. In our world, R has a very amazing tradition. All of these libraries, they contain not only a user documentation, they contain something called vignettes. You can just use the help command in R and it will give you fairly good documentation. But you can use something called the vignettes. These are a treasure trove of helpful guidance on how to use these libraries. And then there is obviously the R documentation website. Here we go. You can go here and you can search for example, any package. For example, here, there is a new package called Cytominer, top 5 package. Let's go and see the top 5 packages. What are the top 5 packages? There is a package called Open Land. What it is? Tool for the analysis of land use and cover. It's a time series package. Right. So, well, you see how well it is documented with examples and graphs and so forth. And quite often the code that you need is all there, right? In the open, waiting for you to use it. What will happen is this will be your starter code and then you'll add things to it. Are we together, guys? Huh? So this world of data science is highly, very well documented. There is a concept of literate programming, which means that instead of explaining what the machine should do, which is what people do when they write code and they put comments, your entire code should be aimed at, in your documentation, the whole notebook, the Jupyter notebooks and R Markdown notebooks, should instead be geared towards explaining to another data scientist what is it that you have done in a reproducible manner. Give the explanation, show your analysis. You should be able to run the analysis, have reproducible results, And so that is a big theme in data science. So anyway, that is that. So I've given the documentations here. Likewise, now there is a lovely journal. Okay, there are two more things. There is something called CTAN task views. If you want to say, hey, I want to do multivariate analysis, which is what we're doing, where do I go and look at it? What are the best libraries available there? So CTAN, which is a repository of all these libraries, they have spent some time curating the best of the libraries for each of the tasks. So you can just go there and pick what you need for each of the purposes. It is as simple as that. Not only are they there, somebody has taken time to put it together. There is a lovely journal that comes out about twice a year. It contains articles, and those articles are generally high quality. Let's go and check what is there today. Journal, right? So let's look at the current issue. How do you connect R with D3 for dynamic graphs? Oh, very good. D3 is very, very popular. Let's go and see what these people have done to connect R with D3. This is it. It is here. It is saying this. I can open this. And I hope you guys can see, guys, that these are not just shoddy documentation. These are very well written articles explaining things. You know, there is a library called TourR, and using this you can integrate D3 into your work, right? Into your R code. Welcome to the TourR Shiny app powered by D3. So he's given an example. It's pretty extensive. Now you can just use this. You like it, and you can use it. And then there is everything is there, bibliography and everything. Right? So in other words, these are very well done documentation and journals in this space. Likewise, in the Python world, Python is a younger, data science in Python is a younger enterprise. Almost all the documentation is just online. So the big libraries, PyTorch, you go to this. Fast AI, they have a course. At some point, I highly recommend you guys to do that, but not now. Or if you want to get started, why not? How would I learn TensorFlow? So I put it in this document. All you have to do is click it. And likewise, scikit-learn, which is something we'll do as soon as we get into machine learning. Pandas, we're already familiar with now. And NumPy, SciPy. So just look at these libraries. Sooner or later, you will, by the way, there's a typo, it should be beautiful soup. You will become familiar with these. By the way, as you guys read this document, if you find typos, do please post it to Slack. So this is it. And then I don't think I have anything else. The rest is bibliography. This is a collection of all the references that I made in this doc. So guys, this is a walkthrough of that. When you do this, then I would like you to try it before I post. Now, I will post the solution R notebooks and Python notebooks. Are you guys ready? Like, should I post the solution, or do you guys need some more time to do the labs? Do all these analysis on your own. Any feedback, guys?
Give us some time to try, Asif. Yeah.
Okay. So take another week, and then next week I'll release the solutions to all of those exploratory analysis. So guys, I'd like to take a, should we take a 5 minutes break or 10 minutes break, drink water and so forth, and then let's get back to theory. How about that? Let's finish our bias, variance, trade-off, and regression. Today I want to be done with regression. Let's take another hour and finish it off. Are you guys game for it?
Sure. Yeah.
Sure, sounds good.
All right. So I'm stopping the recording, pausing the recording for about 10 minutes. We'll regroup at 9:40. All right, guys, let's resume with the lecture part now. If you can see my screen, we are talking about linear regression. So you realize that the error term we wrote down, I took the liberty of writing this before. So the error term is this. Right? And let me remove the mouse from here. This is the error term. Now, to go back and recapitulate our theory, suppose this is your hypothesis. And this is your x-axis, sale of ice cream, the temperature, and the y-axis is sale of ice cream, sale of ice cream. This is the example we took, and let us just mark the data point somewhere around this. I think enough data points. So we realize that this is, maybe the mouse has become too big now. Are you guys able to see the pointer?
It's not visible.
No.
It's not visible. So my mouse is not visible. Huh? Okay. Guys, I'll have to figure out how to make it work in WebEx. But I am just basically making drawings in the graph. So these are residues, guys. So we remember that, right? And so this is nothing but the sum of residue squared. Okay. Now I explained to you something called the line assumptions or the Gauss-Markov assumptions and so forth. And while that was correct for one dimension, when we go to many features, the more formal statement of those Gauss-Markov assumption, it is more complicated than that. And we will talk about that at some point, but not today. Today, we want to finish this. So guys, we say that the sale of ice cream does depend on the temperature. That's a hypothesis. Baseline hypothesis is there is some relationship. And it's a linear relationship and we are finding it. What is the opposite of that hypothesis? Like when would the entire modeling exercise be useless?
The sale of ice cream is not dependent on temperature.
Exactly. When temperature has nothing to do with the sale of ice cream. So for example, if my x-axis was not temperature, but it was the number of penguins who jumped into the Antarctica, in Antarctica jumped off into the sea on that given day, well, you would plausibly argue that that has nothing to do with the sale of ice cream on your beach, isn't it? So just because you're given data like X and Y, you should not just assume that Y is equal to some function of X, right? Up to an error term. You should not just assume that. That may or may not be true. So the null hypothesis is that there is no relationship. There is no relationship. No relationship. Relationship between features and target variable. Right? Features X and target variable Y. There is no relationship at all. So if there is no relationship, what is the best Y that you can predict? What would be the Y value that you would like to predict? You say there is no relationship. So what is the best I can do in predicting the value of Y? Anybody would like to guess?
Random.
Use the previous y value.
Yeah, what you can do is you can just take an approach which just takes the average of the middle of all the Y values, right? Just go and take the average value, Y bar. Right? So irrespective of what the X is, predict Y bar. Isn't it? So this green line is the null hypothesis. Now, you would agree that the green line would have its own error term of the null. Let me write null with a phi symbol. This is a symbol for null, I suppose. Is basically the sum squared residues of I, yi minus y bar square, isn't it? Not the prediction, because your prediction is always not y bar, in fact, no y, just the y bar. Are we together, guys? And so any model that you build, anything that learns from the data, any hypothesis that you build, what should be the baseline criteria that it is successful, that it has learned something? Would somebody like to guess that? What would be a proof that your model is actually worth it? What is a baseline condition you can think of?
Better than null hypothesis.
Yeah, better than null hypothesis, right? So you would like to say that your this guy, E of your hypothesis is greater than what? Greater than E of the null hypothesis, isn't it? In fact, sorry, not greater, sorry, now smaller. I apologize. It should be smaller, isn't it? Your hypothesis should make smaller errors in prediction than the null hypothesis. Would you agree that this is a baseline condition that you would
Yes.
have in models? The question is, and we will use this baseline to define a term which is defined. Now, suppose your error hypothesis is 0. You have no errors in your prediction. Would that be a good model or a bad model?
Unrealistic.
Unrealistic, but let's say in this term, you would say close to 0. You would say, well, that sounds pretty good. On the other hand, if your E hypothesis is the same as the null hypothesis, you would say it's not doing any better. So we need a number, a measure which is equal to 0 when E hypothesis is equal to E null hypothesis. And let us say it goes up to how good the measure is, a measure of goodness when E hypothesis. Well, the error can at most be epsilon or 0. The smaller the hypothesis error, because then you have gone from certain null hypothesis error to absolutely 0. So let's have a sliding scale. 0 is it's pathetic. 1 is a great model. So any real hypothesis, realistic hypothesis, should be between 0 and 1. So if you just observe this, you can see that the improvement, so a measure of improvement, a measure of improvement is, would you say that this would be a measure of improvement? How much smaller is the null hypothesis, I mean, the hypothesis compared to the null hypothesis in errors? Would you agree, right? This would give you some measure. If hypothesis error is the same as null hypothesis error, you have no improvement. Guys, does it make sense?
Yes.
Yes.
And so what we do is we take this as a measure, except that it makes sense to divide it by the null hypothesis. Why? Because it gives you a proportionate improvement. Proportion, I'm sure I've misspelled it, proportion of error reduction. Would you agree with that, right? And now let's see, does it fulfill this green criteria? When error hypothesis is equal to null, hypothesis error is the same as null hypothesis error, we get what? 0 in the numerator. And so this becomes 0. That looks right. When hypothesis error is absolutely 0 in itself, E5 minus 0 over E5 would become 1. This looks to be a good measure. And indeed, it is a good measure. There is a name for this measure. This measure, so let me write it. It is the famous R squared. We call it the R squared, and for historic reasons, of your hypothesis. And E. There is a name for it. It is called the coefficient of determination. Are we together? It's a fancy word, and R squared is in linear regression, and only for linear regression, it is perhaps the most often used measure. Are we clear, guys? Right? So this is R squared. Now, yeah, go ahead.
Can we really quick go through the hypothesis, how it is, it should be less than that?
Yes, very good question. So let's take this example. Do you realize that the green line, let's see the mistakes of the green line. The green line is making big, oh, sorry, green. Why is the green not? Maybe, let me fix the color so these notes are there. So look at the errors from the green line. Do you see how much bigger errors it's making? The green line is making these big errors. Do you see that, guys, that in average, the green line makes bigger mistakes, isn't it? That's the whole point. Its predictions are vastly wrong. Was that Sapna who asked this question?
No, it's Manisha.
Manisha, so do you see that, right? That the green line is way off. It is just saying the same answer, irrespective of what the X value is, whatever the temperature is. It says you're going to sell this Y bar amount of that. So it will make much bigger errors. It just has learned nothing from the data.
Saying that the sale of ice cream will be the same no matter what temperature.
Exactly. So you would assume that if you have a theory, if you have a hypothesis or a model about the true relationship, it should beat the null hypothesis, right? It should beat the no relationship story, isn't it? Which is why we say that the error of the hypothesis has to be less than the error of the null hypothesis. Otherwise, this hypothesis is meaningless, isn't it?
So hypothesis is the error of a hypothesis is just a random selection?
No, of this line, of this best fit line that you made through the data. Right? So what you do is, remember, you try to find the best line going through the data. But if it is best, it better improve upon. Right? Otherwise, what is the meaning of best? Right. Best line through data should at least improve and have lesser mistakes, lesser error compared to the null hypothesis. Is that clear?
Question.
Sir,
if you generate a new hypothesis, does that mean the next time you want to generate another hypothesis, you have to reset the null hypothesis, or do you?
The null hypothesis remains the same. It is the flat line average. So what really happens is that the machine will leave the null hypothesis alone. It will try to find the best fit line to the data. Remember the gradient descent we talked about?
Yes, sir.
Ultimately find the best line to the data. But then if we say, all right, now that I've filled it, let me see how good is my model. The moment you ask how good is a model, one of the easiest things, or the first thing to look at, is how much have you improved upon the errors of the null hypothesis.
Oh, so the null hypothesis will stay static during the learning process?
Yes, it stays static because it is just a fixed thing.
Okay, so you don't reset the null.
No, you don't.
Fixed another fixed.
Yes, you don't do that. And so we have therefore this as a measure model. Unfortunately, this measure, people are so fixated on this, it's so influential. They get a good R squared and they start jumping around thinking that they have made a good model. But actually, and one of the lessons I want to mention is, one metric does not prove that you have a good model. There can always be a better model. The fact that you got a R squared, which is greater than 0, means you are on the right track. It may not necessarily mean that what you're doing is the best thing doable. There may still be reducible errors by using a better hypothesis. Right? I'll give you an illustration. Suppose your data is like this. And this is part of your lab, by the way, next time's lab. Suppose your data is like this. And how many bends there are in the data, guys? 2 bends, right? And so if you try to fit a straight line, the best straight line would be something like this. Let me call it the hypothesis 1, the best straight line hypothesis, right? Order 1, linear hypothesis. Now you realize that this linear hypothesis will make less mistakes than the null hypothesis, right? So R squared of the H1 will be greater than 0 for sure. It would have made some improvement upon the null hypothesis. But is this the best hypothesis? Or perhaps somebody can come and draw a hypothesis, a third degree polynomial hypothesis. 2 bends means third degree, right? So let me call this H3. What do you say? What you will find that R square of H3 is greater than R square of H1, which is both greater than 0, right? So H1 is moving in the right direction. H3 is even more progress in the right direction, isn't it, guys? So you have to know that just because you got an R squared, which is greater than 0, doesn't mean that you have a good model. You should look at other metrics. So what other metrics we're looking at, we will talk about when we do the lab part of it. But today I want to quickly end with a topic we left unfinished last time, which was the topic of, does somebody remember what was the topic?
Bias variance.
What is a bias variance trade-off? So what happens is, and when you build a model, let's say that you look at this model. Let me just take this as an example. This third degree polynomial. See, I could have fit an even more complicated model. Let me take a more complicated model. More colors. What color should I take? Yellow. Maybe yellow. Suppose I took a model of 4th degree, of 7th degree. Something like this. Right, let me call it H7. Do you think between the white hypothesis, the H1 and H3 and H7, which do you think is the best? Anyone?
3.
The H3 is the best. But guess which will give you the lowest R squared if you try to compute the data?
7.
Yes, what will happen is paradoxically, you will find that R squared of H7 will be greater than R squared of H3 is greater than R squared of H1. And all of them will be greater than 0. Well, you say, well, that sounds unfair. So this R squared thing, this coefficient of determination is misleading us now, isn't it? So what happened? This is an example of why you shouldn't trust just the R squared. But there is more. You say that, okay, I can do a game. First thing I do is I take the data and I break it up into the trained data and the test data. Right. And by the way, in Python and R, these are one-liners. Easily it will take your data and create 2 subsets of data, one for training, one for testing. So what you do is you fit your model to the trained data, fit model.
Asif, quick thing, because visually looking at it, the R square of H7 seems to be doing much worse than even the R square of H1.
Yeah, it's because I should have cheated a little bit on a lot of points on it. Now, what do you say now?
Okay.
Yeah, okay. So there you go. Right? So what it is doing is it's fitting onto the noise. The yellow line fits onto points that are actually, while most of the points are going through this, it is fitting onto the, it's too flexible basically. Obviously, my depiction is not so good, but the point that I'm trying to make is a yellow line is too flexible. It will just try to fit to the data, overfit to the data, with the overfitting problem. Right? So now the thing is, you need a test to tell that you are overfitting. So what you do is you find the error of each hypothesis on the train, and you compare it to the error on the test. Oh well, that is bad because this is train and okay, let me just use train and test. So now one of two things will happen. For the red hypothesis, because you have randomly split the data, what do you expect? E train to be much less than a test or approximately the same as test. It will be more or less the same because you have a good model, right? What will happen for the white one is that, again, the same thing will be true. E train and E test will be high. E train will be more or less E test. But for the yellow one, something weird will happen. What will happen is E train will be much, much less than E test. Means your model did very well. It just sort of comes out with flying colors on the training data. But the moment you try it with the test data, it blows up in your face. The test error is very high. Are we together, guys? Right. That is a sign, and this is a sign you should watch out for. Because when this happened, probably overfit. Overfit. Fit to data. You have overfit your model to the data. And that is what we are going to avoid. Right? Now, I said that the line hypothesis, let's go back and review our bias variance trade-off. The line hypothesis, is it simpler than the ground truth? Yellow, the green lines being the ground truth, the data. Would you say that the line hypothesis is simpler than the actual reality or more complex than the actual reality?
Simple.
Simpler, right? So it is making mistakes because it is very inflexible. It is just a straight line no matter what. And that is the best straight line you can capture. Right? And so you say that the hypothesis, first hypothesis, suffers from, now let me use the white color. The hypothesis one, I'll just write it down here. Hypothesis one suffers from excessive bias error. Right? It is the errors of being simpler than reality, being too stiff is this. Hypothesis 7 suffers from high variance errors. Right? Overfitting errors. So now let me give you what happens. There's a trade-off actually. So suppose you have data, you don't know that a third degree polynomial would be best. What you do is you take the errors. And if you look at the training error, what will happen is that as your, training error, no, this is not the x-axis. This is the training error. This is the complexity of the model. Think of as degree polynomial, nth degree. That would be one example of it. Degree polynomial. That's one example. Because if you do polynomial regression, the higher the degree of the polynomial, the more the complexity of your model. So what will happen is that as you train, your training error will keep on decreasing. Are we together, guys? Right. But your test error will behave quite differently, actually. Your test error will behave like this. Now, let's try to understand what happened. Why is this blue line continuously going down, the training error going down, right? With more and more complex models or higher degree polynomial? How would you explain it? Anyone, guys?
Fitting to noise.
Yeah, it's fitting to noise. It's very flexible. The more flexible you make it, the more it will, reduce the errors by going through more and more points, or getting closer to as many points as possible, isn't it? But then, why is the test error going up after some time? Because you realize that after a little while, it is overfitting to the data, isn't it, guys? But it has overfit to the training data. Means because the test data is different from training data, right? This test data is separate from training data. If you only listen to training data contains noise. If you overfit to the noise, then on the test data, you won't do so well. Your error rate will start going. Are we understanding this concept? Anybody? Right?
Sir, so are there are there certain data that you can actually prefer more variance errors than bias errors? Or are you really supposed to just meet somewhere in the middle?
See, this is a very good question. Your question, I'll rephrase it. Is there any data in which you say, let there be variance errors? No, you want to reduce the error. But there is a different answer to your question. When would you make more complicated models? This is one of the central problems. When will you think that a very complex model, it is okay to build? And I don't worry about overfitting. The answer to that is big data. You have a lot of data. Variance errors also disappear. Not only the bias errors disappear, variance errors disappear in complex models. So both bias and variance begin to vanish. There won't be a situation where you would prefer one kind of error more than the other. But when you have a lot of data, you have the luxury of considering much more complex models. And you can see this. The deep neural networks are very complex models. Their hypothesis space, parameter space, is sometimes 500 million parameters. We are having difficulty developing intuition here today in one dimension. Can you imagine developing intuition in parameter space that actually two dimensions, beta naught, beta 1? But can you imagine developing intuition in 500 million dimensional space? Highly flexible model that can fit to things. But we still dare to go there because, amongst many other reasons, one of the big reasons is we have today a lot of data. So we can tame the problem of variance. By having complex model, we won't have the problem of bias, but we fear the problem of high variance, overfitting. It is a problem. We will always have to deal with overfitting. But the more the data, the more it brings down overfitting.
I see, sir. So my question was really because we're between complexity and trying not to overfit. But are there situations also, let's say you have a two-step machine learning model where the first step you actually want to overfit. Let's say you want to get the boundaries of a picture or something before you get the finer details. Are there situations where you can afford the extra complexity to overfit, or the extra variance errors that come with more complex?
Okay, so bear with me and see if this answers the question. The next thing that I was going to explain. It may answer. If it doesn't, then raise this again. But I understand where you're getting what you're referring to. So guys, let us look at this. The errors come from two sources: the bias errors and the variance errors. So as you increase the complexity, the bias errors reduce. You realize that your model is flexible. So bias errors keep going down. Let me call it bias errors. And we are now talking about on testing data. On testing data. And the same with the bias errors. Are we together, guys? On the test data, actually, let me remove it because you guys are going to refer to these notes. Let me put it in small. Complexity on testing data. So remember the graph on the left is, let me call it B and A. B is on testing data only. Your bias error keeps coming down. Your variance errors keep going up. You agree, right? As you make the model more and more complex, your variance errors will go up. Does this make sense, guys? And because your total error is made up of your, remember the total error is what? E bias squared plus E, actually, let me just say bias squared. Let me just put the bias squared down right here. Bias squared plus E variance plus the irreducible noise. Do you remember this relationship, guys? The real thing is, it is made up of, now we cannot do anything about the epsilon. Can we do anything about epsilon? We can't, right? It is the missing information. But we are playing a game between bias and variance by dialing up the complexity of the model. But the total error is the sum of these two. So what will happen to the total error? The total error will go like, if you add up these two things, it will go like this. Do you see it, guys? Actually, let me use the red line, and because then you will see the total error. Do you see this, guys? That bias error comes down, variance errors goes up. So there will be a particular point, the perfect, where the complexity of your model at this point, let me call this point P. What happens at complexity P? Let me write down at, well, let me write the word down. So the best model that we could fit to the data is at this complexity P, because that is where the trade-off between, given the trade-off between bias and variance. The bias squared. People just say bias variance, but actually it's bias squared. I won't say bias. So this is called the bias variance trade-off. This graph above is the bias variance trade-off. The fact that in reality, as you make your model more and more complex, variance errors will keep rising, bias errors will keep coming down. And so there is an optimal point at which the error would achieve a minima. And that is the model that you're looking for. Because what happens at that point? At that point, the complexity of the model,
Why is bias square?
This is the mathematical thing. If you grind the mathematics, the way the bias is defined, total error is the square of bias plus variance. See, variance is sigma squared, right? Remember? Variance.
Yes, yeah.
So it has the square built in, but bias doesn't have the square built in. That's why you need to square it. Right. The model approximates the complexity of the ground truth. This is an important statement, complexity of the ground truth. Right? And this is the point that when you have met the bias variance trade-off and found the best model, right, that model P, at P, the complexity of the model approximates the complexity of the ground truth. Right? Are we understanding that? I'll be happy to repeat it.
Yeah. So, sir, this is the general truth, no matter if it's or simple data. This is the
Right.
general ruling that
Absolutely.
you want.
And so what happens?
Yes.
You have to take a model, let's say a polynomial regression. Given a line, suppose you take degree 1, you can find the best fit line. You take degree 2, you can use gradient descent to find the best fit parabola and best fit third degree curve and so on and so forth. But what you cannot have machine do easily is tell you what is the best value of n. So that is why in a polynomial regression, n is called the hyperparameter of the model. So remember that in an equation, y is equal to, or y hat is equal to beta naught plus beta 1x, and I'll generalize it to higher degree polynomial, x squared, xn. The parameters are, guess what the parameters are, guys? Beta naught, beta 1, beta n, isn't it? Are we together? These are the hyperparameters, these are the sort of parameters of a hypothesis, isn't it? Right. Polynomial hypothesis. And these are the parameters. But in this, there is a hyperparameter. What is the hyperparameter? What is it that you can't just directly learn by gradient descent? It is n, the degree of the polynomial. Polynomial. Complexity. The more you have the n increases, the more the complexity measure. The more complex the model becomes. What you have to do is you have to successively make polynomial models of higher and higher degrees. But then, when do you stop? The good news is it is easy to stop, because what will happen is your test error will first decrease. The test error decreases, and then it begins to increase. So at this degree, whatever n is, and where n would be 3, let us say, you know that you have reached the ground truth. After this, the moment you notice that your fourth, fifth degree, you notice that errors are increasing, time to stop. You have found the best, isn't it? So you keep on dialing up the complexity while the test error is going down. But after that, the moment you notice that your test error has started going up, you say, now it's time to stop.
So Asif,
right. Go ahead.
In here, the only tunable we have is the degree of variance, right? Biases is anyways being minimized by gradient descent for that degree.
No. Bias is independent of that. Don't confuse the two. See, bias and variance are associated with the complexity of the model. Whatever complexity you take, so suppose you take a fourth degree polynomial, gradient descent will find the best fourth degree polynomial to fit to your data. Are we together?
So if you go back up on the drawing you have,
go
back.
Right. What is?
Yeah, yes. No, that E-train. Yes, this thing, right? So now going back to hypothesis 1, hypothesis 7, and hypothesis 3, right? So we said for hypothesis 3, E-train would nearly be equal to E-test, right? But right, and that is the closest to the truth. So let's forget about that for now.
Right.
Hypothesis 1, which is the white line, we said again E-train will be nearly equal to E-test, but here the bias will be very high.
So what happens is most of the errors, hypothesis 1 is coming from high bias, and you can't do anything about it. You can't learn that from gradient descent. because the best line, it is still the best line. Gradient descent has found hypothesis 1, right? If you insist on a straight line, that is the best straight line that gradient descent will take you to. And that line will suffer from high bias errors.
Yes, that's what I was trying to form up in my mind, that you will get a polynomial or you'll get a what do you call a fit by the best fit using gradient descent for that degree.
For that degree.
And that fit will inherently come with its own bias error, which you cannot.
Bias and variance error, both bias and variance error, but you don't
both
know.
Bias and variance, yeah.
Gradient descent is not able to tell, is this error bias or variance? It's blind to that. All it says is total error, I reduced as much as I could.
So Asif, so there's no variable equation for bias and variance, right?
No, there is an equation, but gradient descent
okay.
doesn't help you. Gradient descent doesn't help you there. It is a recurring problem, guys. In machine learning, at this moment we are doing, we are just learning to crawl before we run. This is linear and polynomial regression. By the way, these are the most effective and with common root. Surprisingly, that this simple models work so often, more often than you think. But even at this level, you already realize that you can fit gradient descent, you can find the best parameter. But hyperparameter means you have to build a lot of models and see which is best. You have to do your bias trade-off. And there is no magic. Think about it this way, practical terms. Somebody has given you a data. You don't know the ground truth, right? You don't know what is the complexity of the data. What can you do? You have no choice but to build models of varying degrees of complexity, try to fit it and see which works best. Where does the bias variance trade-off has the optimal point, isn't it? And then wherever it has optimal point, you look at the complexity, you look at the degree of the polynomial and say, aha, so this is as close to the ground truth as we can be.
So sir, so other hyperparameters would probably be how many degrees you would want to jump.
How many? What we want to jump?
Like how many times you'll move up a degree, or does it automatically just go 1 degree up at a time?
Usually do that. See, what happens is that polynomial regression, right? The story is that you would take first degree, second degree, third degree, and you would keep making a plot like this. Where is that plot? You will keep making a plot like this. You will be just observing the test error. And in the beginning, the test error will keep going down. Then it will reach people, in this case, at degree 3, you will get the best or the lowest test error. And after that, you go to degree 4 and 5, and again, the test error begins to climb up. The moment it begins to climb up, you say, okay, it's time to stop.
Right.
I found the best model at degree 3.
My question is, sir, if you're working with big data, sir, would it be time consuming to start with the low degrees if you know that you'll be moving high degrees, or is that really part of the process?
Yeah, see, the big data complexifies the situation. There are some people who would say that, see, we have big data, so we can start with a very complex model, and the big data will tame the variance errors also. A bias won't be there in a less likely to be there in a complex model, and variance errors will be suppressed by a lot of, right? And we'll do that exercise. We'll see that. But therefore, start with really complex model. It has become very fashionable, by the way, these days. Even it's like, you have to put a nail in the wall. Instead of using a hammer, you go and get the biggest earth mover, right? Or something like that. It doesn't make sense. So people, no matter what, they will always pull out very sophisticated models. They'll start talking, I suppose, gradient boosting or random forest, deep neural net. The thing that's wrong with it, the problem is the more complex the model you build, the more human beings interpret it. We we lose interpretability.
Mhm.
I'll give an example, or even manageability. If I told you, you are a diabetic, say, right? You go to your doctor and you say, what should I do? My sugar has gone up, and how do I bring my sugar down and manage my sugar? And the doctor gives you, he gives you 10, so there are 10 parameters in the model. And he begins to say that in the morning, your breakfast should be no more than 400 calories and no less than 200 calories. Your lunch must be this. Between breakfast and lunch, by the way, remember to walk 1.5 miles. And you give a very complex set of instructions. You have set the value of 10 parameters for that and say you must sleep this much and so forth. Would you go to that doctor or would you go to another doctor who has a 2-parameter model? He will say exercise more and eat less. So think about it. Which of the two models is more effective? Are you getting the point?
Yes, sir.
It's real. We need the simplest. It is called the Occam's razor principle. Occam's razor principle says that for a given data, there can be a whole set of very complex explanations. But the simplest explanation is the definition of the correct one. Right? In science, there are no correct answers, but we define correct answers. The simplest explanation that works. And that's the Occam's razor principle. But even in the presence of big data, it is our responsibility as data scientists to search for the simplest model that does work. And that is of tremendous practical applicability. And at some point, I'll tell you stories from literally the law courts of companies getting sued because they made complex, opaque models. And they led to all sorts of biases. Biases in the political sense, gender bias, discrimination, race discrimination, and so on and so forth. And those guys were not aware of it. They weren't aware because the entire model was so complex and so opaque that, well, it was that. And that begged the question that why did you not try to fit simpler models to the data? So actually, from a legal perspective, a lot of these very fancy complicated models are not even acceptable in certain areas. You have to put to simpler models that work. So that is another aspect of the story from a real life situation.
Sure. This is assuming you don't drop data, right? You're still using the same data. It's just the model. It's just the model is simple.
That's right.
Okay. Thank you.
All right, guys. Any other questions? So guys, we have go ahead, please.
Asif, just to clarify, you have given a higher level equation, but you're saying that there will be a certain equation through which you can get the bias square itself. Like when you choose a n-degree polynomial, you can still get the pieces of the equation, which is the bias, variance, and the floor error. All three of them you can get it through some.
Yeah, see, you can compute the bias and variance. These are just formulas. You can do that. So, for example, at this model, right? Sorry, where am I at this point? This point is behaving very strangely. Why is it behaving strangely? Give me a second, guys. Yeah, this point. At this point, what happens? You can measure the bias error. This much is the bias error, isn't it? Sorry, this much is the variance error. Where is the bias error? Okay, my line was really crooked. Bias error. This is not bias error. The bias error was here. I don't know what happened to my line. So this is bias error, right? This line. So you can see that I can measure the bias error and I can measure the variance error, isn't it? They are the same. The bias and variance errors are pretty much reaching
I
us.
thought you can only measure the red color, right? The total error is it's the observable error.
Yeah. So this is it. You can
know
do in gradient descent during the gradient descent process. But once you have done your gradient descent, you want to see what is really happening. See, the trouble is you have only test data. Just having the formulas of bias and variance doesn't prove very useful. For linear models, it works. In real life situations, you wouldn't know. You really wouldn't know. With the deep neural networks, you don't know what's happening.
So, sir, in real life, the goal is not always to hit point P. It's just to reach the model P that's the most effective for your use case.
Exactly. You find the model that is most. You're in search of the best point given the bias variance trade-off. Where does the trade-off work out? So, guys, in practical terms, you often do that. Right? For example, the more we exercise, the better our health. But the more time we spend exercises, the less time we have to play with our kids, and our kids become unhappy, isn't it? So, they say that after coming back from work, you do have a trade-off. So at some point, but if you don't exercise at all, you'll get sick. So at some point, you have to find a trade-off. What amount of exercise you can do and get the maximum health. I mean, as much health as needed. At the same time, you get time to play with your kids. We make those trade-offs all the time. So it is somewhat like that. Bias and variance trade-offs are very real trade-offs we face in our life. Any other questions, guys? This has been a long day. So a couple of action items, guys. If you're not on Slack, please reach out to me or reach out to Pachi or Dennis, and they will add you to the right channels, the TAs. And the other thing is, do follow Slack. I'll be posting messages there. You must be receiving mailing messages. I will send out another survey after this class to see how you understood each of the concepts. Whatever concepts are not very clear, I'll always. So with those words, I'll conclude today's session. Those of you, I'll at least conclude the recording of today's session. After that, I'll make it an informal QA. Those of you who want to stay back are most welcome to stay back. And then we will do